Welcome to damped free spring mass systems. So recall spring mass systems have displacement from equilibrium modeled by m y double prime plus cy prime plus ky equals f, or f of t, where m is the mass, c is the damping coefficient, k is the spring constant, and F is the external force. So free spring mass systems with damping, there is no external force. So in a free system, the external force is 0. As a result, the equation becomes a homogeneous equation. So we are looking at my double prime plus cy prime plus ky equals 0. So any problem of this type, we can just go ahead and solve for the homogeneous solution. This is a second order linear equation with constant coefficients. So solving for this general solution, we go to our characteristic equation. And we have mr squared plus cr plus k equals 0. So using the quadratic formula, we have that r should be equal to negative c plus or minus the square root of c squared minus 4 times m times k all over 2m. And depending on what happens with that c squared minus 4mk, we can get 3 different cases. So this results in 3 different types of cases. So case 1 is what we refer to as underdamped. Underdamped situation is the case where, so if c squared minus 4mk is less than 0, or in other words, if c squared is less than 4mk, then r is a complex number. And our solutions will take the form y is equal to C1 e to the negative c over 2m times t times cosine of something. I'm just going to do cosine of omega naught t plus c2 e to the negative c over 2m t sine of omega naught t. And here, omega naught is the square root of 4mk minus c squared over 2m. So if we're in this case where we have the imaginary solutions to our characteristic equation, then we get cosine and sine involved in our solution. We have oscillating. So the system oscillates. C and M are both positive. So the negative c over 2m is negative. And so the amplitude shrinks over time. So the system oscillates. And then since C and M are both positive and we have negative c over 2m is less than 0, then we have that the amplitude decays over time or decreases over time. And it decreases exponentially. Over time. So this is a case where we essentially have exponential function as our bounds, and then we have our oscillation. And over time, it essentially goes to the equilibrium state. So the limit as of y of t as t goes to infinity is just 0, and the system heads towards equilibrium. Case 2. Is overdamped. So in this case, if we're overdamped, we have, again, this occurs when c squared minus 4km is greater than 0, it's positive. This means that the characteristic equation has distinct real roots. And in fact, both of those roots will be positive, will be negative. So it'll have distinct real roots, both of which are negative. And so we just get, let's consider them to be R1 and R2, both less than 0. And so what we get then is we have our solution takes the form y is equal to C1 e to a negative number times t plus C2 e to the R2 times t. Again, both of those are negative numbers. Let me update quickly. So this is our solution. Again, both R1 and R2 are negative, so we just have exponential decay. So note R1 and R2 are both negative. So we have exponential decay. Again, the limit as t goes to infinity of y of t will be 0. And so the system heads to equilibrium. And in this case, note that there is no oscillation. Essentially, our system just heads in towards equilibrium. And then finally, we have the case which is called critically damped. This is case 3. This is for critically damped. And for critically damped, this occurs when c squared minus 4km equals 0. So in this case, the characteristic equation has repeated root. And the root is just r is equal to negative c over 2m. And so our solution takes the form y is equal to c1 e to the negative c over 2m times t plus c2 t e to the negative c over 2m times t. So this one's not quite an exponential function because we do have that times t. And the way that this appears looks a little different. We wind up with that initial times t can start off overpowering the exponential decay, and then the exponential decay goes ultimately wins out in the end. So we might wind up with something that looks more like this, right, where initially the amplitude grows until then it heads with exponential decay towards equilibrium. So this is in the critically damped case. we can have this special situation. In overdamped, it's just more or less straight exponential decay. And then in an underdamped system, oscillation still occurs. But in all cases, we head towards zero. So once again, the limit as t goes to infinity of y of t is 0. So the system, once again, heads towards equilibrium. And as I noted, there is no oscillation. So these are sort of the 3 cases that we deal with.